So we're starting off with a very quick sketch of the graph of the function between x equals -3 and 3. So I'm going to start with the part of the graph defined for x greater than or equal to 0. So that is a parabola which clearly has a minimum point at 1, 1. Now it has a y-intercept which we can calculate. G of 0 is equal to 2, and that's true for both parts actually. So we've got a y-intercept at 2, and then we are working out this function for values of x up to 3. So g of 3 we can calculate as well, which is equal to 5. So we've got a portion of a parabola that looks like that. Now, for the other part of the graph, do this in a different colour, this part of the graph, g of 0 still equals 2, so we have continuity here at the crossover point, but this other graph is a parabola which has a maximum point at -1, 3. So over here, and we know when x equals -3, g of x equals -1. So we'll have a graph that looks a little bit like that. I'm just going to put in some coordinates. So 1, 1, 3, 5, 0, 2, -1, 3, and over here -3, -1. So I'm actually just going to get rid of a portion of the graph that we have outside of the given set of x values. So part 2 asks us to write down the grade expressions for m of x in the two cases. So x greater than or equal to 0. Now remember, m of x is equal to the gradient of the chord joining a point on the graph, which could be here, for instance, x g of x, and the point 0 g of 0. Now of course g of 0 is equal to 2, so we're looking for an expression for that chord's gradient here. So we can simply say change in y, so g of x minus 2, over change in x, which is just x. But for x greater than or equal to 0, g of x can be replaced by x minus 1 squared plus 1, subtract 2, all over x. And that simplifies to x minus 1 squared minus 1 all over x, which we can simplify this further as needed. Running out of space a little bit. Let's do that over here. So that's x squared minus 2x all over x, or x minus 2, dividing through by the x. And we've now got to do that same calculation for x less than 0. Now for the second part of this, we want to do another gradient calculation, but it's important that we're now looking at a point x g of x on the other portion of the curve and finding the gradient of the tangent there. So for x less than 0, m of x is equal to g of x minus 2 again over the change in x coordinate, which is just x. Now g of x for this portion of the curve is 3 minus x plus 1 all squared minus 2 there, all over x, and then we can simplify this, so this is 1 minus x squared plus 2x plus 1 all over x, and this then simplifies down to give us minus x minus 2. So part 3, very simple. For x greater than 0, we have to find m of x plus 2. Well, we notice that m of x was equal to x minus 2, so we have x minus 2 plus 2, which just equals x. And then for x less than 0, m of x plus 2 will equal negative x minus 2 plus 2, which simplifies to give us negative x. Now, the next part of the question asks us to explain why g has a derivative at 0. Well, we know that g dash 0 we can evaluate using first principles. It is the limit as x approaches 0 of m of x, the gradient of the chord. So it is the limit as x approaches 0 of x minus 2, so as x approaches 0, the gradient equals negative 2. Now, we can use our other definition of m of x as well. Remember, we have two of these, one for x greater than or equal to 0 and one for x less than or equal to 0. So in that case, it's the limit of negative x minus 2, and again, this results in a gradient of negative 2. Now, part 5 is where the serious maths actually starts to appear in this question. This is the difficult bit of the question. So we know that h of x is a cubic with a maximum at point P and a minimum at point x equals q. So that means that h dash of x must involve something like this, x minus p, x minus q, so that when we solve h dash x equals 0, to find the turning points, we get turning points at x equals p and x equals q. Now, we don't know what the scale factor in front of this cubic is, so we're going to need to have to put a constant there of some description. Some sort of stretching scale factor. So I can expand this out just for interest. So a bracket x squared minus p plus q x plus pq. Done a little bit of tidying there as well. And then I can also differentiate a second time to give me h double dash of x, which is equal to a 2x minus p plus q. And that may come in handy. Now, we know that we have these points here. So I'm going to start with x equals p. Now, x equals p is a maximum point, which means that h double dash of p must be less than 0. So let's substitute into h double dash of x, substitute in x equals p. So we have a 2p minus p plus q is less than 0. So a p minus q must be less than 0. Now, we were told earlier on in the question that p is less than q. So because p is less than q, p minus q must be less than 0. And this is a product. It's a multiplied by p minus q. Now, if this part here is negative and you want the product to be negative, that means, by extension, a must be a positive value. Now, does that match what we get when we look at the other point over here, the minimum point? So when x equals q, because we have a minimum point, this tells me that h double dash of q must be greater than 0. So a bracket 2q minus p plus q must be greater than 0. A bracket q minus p must be greater than 0. But again, remember, p is smaller than q. So this tells us that q minus p must be greater than 0. So this bit here must be positive, which means a, again, has got to be positive so that the product of a and q minus p is greater than 0. So a must be a positive value, and this will be important in a minute. So we just identified that h dash of x can be written as a bracket x minus p x minus q to give us the two stationary points that we want, one maximum, one minimum. And we also know that a has got to be a positive value. Now, we're asked to comment on the gradient h dash of x when we're looking at x values which are in between p and q. So x is larger than p but smaller than q. Now, if x is in between these pair of bounds here, this tells us that x minus p must be positive because we know that x is greater than p. But we also know then that x minus q must be negative. So in our derivative formula here, this bracket here is positive, this bracket here must be negative, and we know that a is positive. So the derivative is a product of two positives and one negative, which implies that h dash x must be less than 0, specifically when x lies between p and q. Now this takes us on to part 6, another tricky question. C and D are real numbers and there is a cubic h of x with a maximum at x equals -1 and a minimum at x equals 1. So what I'm going to do is quickly sketch what this cubic might perhaps look like. So what were we told again? We were told that there is a maximum at -1 and a minimum at x equals 1. So might look something like this. We're not really sure. So this is the point 1 and h of 1. So this is y equals h of x. And this point here is -1, h of -1. So we've got some coordinates. And I think we're also given some other information. H dash 0 equals -3c. And h of 0 is equal to d. So that point there is 0, d. So let's just write down h of 0 equals 3c, h dash 0 equals 3c, h of 0 equals d. So let's go back to the information that we're required to find. So we need to show that c is positive and find a formula for h of x in terms of c, d and x. Okay, so this clearly links back to the previous question completely. And we know that h dash of x is equal to a, which is some kind of constant, x plus 1, x minus 1, because we need to get turning points or stationary points at -1 and 1. Now, we're also told that h dash 0 is equal to 3c. So let's substitute in x equals 0, and that gives us a multiplied by 1 multiplied by -1 equals 3c, which then gives us, -3c. Sorry, h dash 0 is -3c. That should have been made more clear earlier on. So that then gives me -a equals -3c. A is equal to 3c. But earlier on, if you remember, we proved that a had to be greater than 0. So that tells us that c has got to be a positive number as well. So we now know that a equals 3c, so we can actually write down h dash x is 3c, x plus 1, x minus 1. I'm going to expand, so I get x squared minus 1, which is a little bit simpler. And then if we want to find out h of x, then obviously we need to integrate to go from h dash of x to h of x. So this gives me 3c, 1/3 x cubed minus x plus a constant, which we're not going to call c, as that will cause some degree of confusion. But we do know that h of 0 is equal to d, so that then tells you that the constant must equal d, and this then gives us h of x is equal to c x cubed minus 3c x plus d. And that's our question complete, as we found h of x in terms of c, d and x. There is one last part here, another tricky thing to think about. Show that there are no values of c and d such that the graphs of y equals g of x right from the beginning and y equals h of x are the same. So what do we remember? We know that h dash 0 is equal to -3c, we were given that. And we also know that g dash 0 equals -2, and that's from, I think, part 4 of the question. So these two pieces of information will give us c equals 2/3, as h dash 0 equals g dash 0. Now, what else do we know from earlier on? We were also given the information h of 0 is equal to d, but we also know that g of 0 equals 2. So from here, this tells us that d would equal 2, because of course if the two functions are equal, h of 0 would have to equal g of 0. So that then tells us that we can identify our function h of x. So going back up to here, we know that h of x would equal 2/3 x cubed minus 2 x plus 2. So let's just double check this with some other information we have. What does this result here give us for h of 1? So h of 1 would be equal to 2/3 minus 2 plus 2, which would equal, well, 2/3. But that is not equal to g of 1, which we know is equal to 1 from the beginning of the question. So that then tells us that h of x cannot be equal to g of x.